Hi, it's Kate, and this is the second video for week 13 of Math 23. First, let's talk about the equality of crossed partial derivatives, or what some refer to as mixed partials. U is an open subset of Rn. F, the function, maps from Rn to R. It's differentiable at a point A and has the property that each of its partial derivatives is also differentiable at A. Then, what we can conclude is if we take the derivative with respect to the ith variable and then with respect to the jth variable, it would be the same as if we took the derivative first with respect to the jth variable and then with respect to the ith variable. The proof consists in using the mean value theorem to show the following. We'll be talking more about this in class, but really we'll be using this primary result. For instance, if you took the derivative with respect to x and then with respect to y of a particular function, it would be the same answer as if you took the derivative first with respect to y and then with respect to x. The fact is that order doesn't matter, but only if f is differentiable at a and each of its partial derivatives is also differentiable at a. Let's take a look of why this is particularly useful. Well, we have a vector field. Here it is. The vector field f maps from Rn to Rn. You may never have really seen a vector field before, but that's okay. All it does is it assigns a vector to every single point. That's what its quote-unquote function value basically is, a vector. All right, let's scroll down a bit. So we have our vector field. The first question is, what's the derivative of a vector field and what does it look like? Well, if we're dealing with 3 dimensions, saying that our vector field f has 3 different components here. These are called the component functions. So whenever I say component functions, I mean the function that governs the first component of the vector, the function that governs the second component, the third component, all the way down to the nth component. In this case, we only have 3. But say we have 3 component functions, then the derivative of this vector field is going to be, okay, up here in this top row, we're only dealing with the first component function. This is going to be the derivative with respect to the first variable, the derivative with respect to the second, the derivative with respect to the third, and then this row will just be dealing with the second component function, the derivative with respect to the first variable, the derivative with respect to the second variable, the derivative with respect to the third variable, and down here in the bottom row, but only dealing with the third component function. It's convenient to define this vector as del. Del is an operator. It's not really a vector. What d1, d2, d3 really mean are their actions or their commands. This means take the derivative with respect to the first variable. This means take the derivative with respect to the second variable. This means take the derivative with respect to the third variable. So if we're trying to compute the gradient of a function where, well, the gradient of a function is a vector where it has the partial with respect to the first variable in the first component, the partial with respect to y as the second variable in the second component, partial with respect to the third variable in the third component, this is what you end up getting. So when we write this as del f, it is the gradient of f. It's basically del multiplied by f, as if we treated f, the function, as some sort of scalar. We would bring it inside and then have d1, the action of taking the derivative with respect to the first variable, acting on f. d2, the action of taking the derivative with respect to the second variable, acting on f, and so on and so forth. What's really useful is that we can define 2 big properties of vector fields using del, this operator. One is curl. If we take del and cross it with our vector field, we end up with, well, here it is written out, we end up with this new vector, which is, oh gosh, if we didn't have this shortcut of taking del and crossing it with f, there'd be almost no way to really remember, pardon me, really remember the order of which component functions we're talking about, which derivatives we're taking. It would be a giant mess. So you can see how del crossed with f is a really useful way to calculate this vector, curl. There's also divergence of a vector field, which is del dotted with f. Note that this is a vector. This is a scalar valued function. This is a vector valued function. This is a scalar valued function. Here we have the divergence of a vector field is the equivalent of taking the derivative with respect to the first variable of the first component function plus the derivative with respect to the second variable of the second component function plus the derivative with respect to the third variable of the third component function. So del really comes in handy, especially when defining this notion of curl and this notion of divergence. What's interesting is that there are two major equalities that hold, and the proof becomes really easy once you understand that mixed partials are equal under particular conditions. So what are those? Well, we have that the curl of the gradient of f is 0. We also have that the divergence of the curl of the vector field f is 0. The way to do that is strictly by brute force. Actually go about computing these, and you'll end up with some equal mixed partials being subtracted from each other. And so these equal mixed partials that we mentioned in the previous section will cancel each other out, and you'll be left with 0. Now, what exactly are curl and divergence? Let's take a look on the next page. Now, the significance of divergence and curl. Paul's R-script video is very, very helpful and talks about this in a bit more depth with some of the calculations about how to determine some of these expectations. But let's talk a little bit about the introduction here. It's sort of difficult to explain a lot about divergence and curl without multiple integration, but like Math 25, we hold off on discussing integration until the second semester of this course. But the powers that be they would like you to have seen divergence and curl by the end of the fall semester. So this is as much as you really need to know about divergence and curl to help you out and have it not be a completely new topic in any of the other courses you may be considering taking. Well, let's talk about this derivative of vector field first. The derivative of a vector field is itself a vector field. It acts on an increment vector h, and it produces df of a acting on h. At a specified point A, it is a linear function of h represented by a square matrix. So here is an example of our plot of what happens when df of a acts on all different increment vectors within this. I mean, these are pretty small increments that we're looking at, but this plot is the vector field of the derivative of f. It looks outward moving, as in it's moving away from the origin. That has something to do with the divergence. And in general, the arrows are moving in a counterclockwise direction. They seem to be going like this, which has to do with the curl. Now consider a random increment vector h. It's of fixed length, but it could be pointing in any particular direction. We're going to choose the length so that the length of h, this increment vector, is fixed. It's going to be n. So for n equals 2, h1 squared plus h2 squared, the two components of this increment vector, will be equal to 2. On average, h1 squared and h2 squared should be equal, so each has an expected value of 1. Which we've just restated here. Since h1 and h2 are equally likely to either be the same sign or the opposite sign, the expectation of their product is going to be 0. Paul walks through a really nice way of showing this expectation using R in the R script, so do check that out. Alright, so out means that on average, df acting on h has a positive component along h, or df acting on h dotted with h, the dot product between those two vectors, is greater than 0. So it's easy to show that the expectation of this dot product is equal to the divergence. So for n equals 2, we end up with the derivative of this vector field written like this. The derivative of the vector field acting on h is written like this. So the derivative of the vector field acting on h dotted with h ends up being this entire expression. And the expectation of this quantity is just going to be, well, h1, h2, both of these go to 0. h1 squared's expectation and h2 squared's expectation is 1, so df of h dotted with h, the expectation of this is going to be d1f1 plus d2f2. The derivative with respect to the first variable of the first component function plus the derivative with respect to the second variable of the second component function, that's the divergence of f. Well, now what does counterclockwise mean? Let's scroll down a bit. Well, this means that, on average, the matrix whose first column is H and whose second column is DF acting on H has a positive determinant. Well, how can we show that? Well, we can show that the expectation of the determinant of this matrix that we just sort of constructed in our head, where the first column is H and the second column is DF acting on H, is equal to D1F2 minus D2F1. Well, in 3 dimensions, and we actually do that in the R script, so please also check that out. In 3 dimensions, if DF acting on H is on average along the same line as H, then the cross product is going to be equal to 0. And so we can show that the expectation of DF acting on H crossed with H is going to be equal to the curl of F using these 2 properties. Very similarly to how we showed that this was equal to the divergence, the expectation of this quantity was equal to the divergence of F. It's quite interesting, in fact. But again, we actually sort of do an approximation of the expectation using 10,000 randomly generated increment vectors H in the R script, and I really encourage you to work through that and run it on your own on your computer. It's pretty fun.